Okay, so carrying on the May 2017 paper, onto waves. Outline what is meant by the principle of superposition. Now this is when two waves meet and they basically add up. So it's the sum of the displacements of each wave. And we talked later on about construction destructive interference. Classic. Next one, double slit, one of our core practicals. So we've got a red laser light is incident on a double slit with a separation. It's given us the slit separation of 0.3 millimeters. Be careful with that. So straight away that has given us the little d in our equation. Okay, this should now be triggering thoughts in your head. Lambda, where this is S, sorry, Mr. Knight, where this is our S, this is our little d, this is our big D. So we've been given slit separation and a double slit interference pattern observed on a screen 2.4 meters from the slits. The distance between successive maxima on the screen is 4.7, so it's just from one maxima to another. So it's given us our S to be 4.7 millimeters. Okay. Now this should be fairly straightforward. It's going to ask, the only thing left is going to ask for wavelength. So it says calculate the wavelength of the light. There's a little trick here as well. It's red light. We know that, you should know that's around 600 to 700 nanometers. So that's where our answer should lie. So we're using our double slit equation. S is equal to lambda over D. We want to find the wavelength, therefore SD is equal to our wavelength. Now, tip is the units, get them all to meters. So our slit separation is 4.7 millimeters, 10 to the minus 3, times by our slit separation, 0.35 millimeters. And they are all separated by the big D of 2.4. Calculate that through, and that gives us a wavelength of 6.9 times 10 to the minus 7 meters, which is a good rough check, which is about 600 nanometers. Okay, now moving on, it says explain. Oh, sorry, I'm just going to try and line up my camera. Explain the change in appearance of the interference pattern when the red light is changed with one of green light. Well, let's go back to our rearranged equation. Lambda is equal to SD over D. So what this question is asking for is the interference pattern. Well, that is our fringe spacing, that is our S. So how does wavelength affect S? Well, they're directly proportional, okay? So lambda is directly proportional to S. So what happens is, you need to know that green light actually has a lower wavelength, because green light has a lower wavelength, and if the wavelength goes down, the fringe spacings will become closer. They're closer together. So you're going to get still a central maxima, but then you're going to get closer together. Observed lines. Now then it says one of the slits is covered up. Well, what that does is that is no longer double slit. It's now you're thinking about a single slit. So what this question's basically asking for is, tell me what a single slit diffraction gradient, or so my diffraction pattern actually looks like. So what we're looking for here, we still would have a bright central maxima, and then we have a decreased intensity pattern. So then your outer maximas have a lower intensity. And this, actually, you could also say the central fringe is actually wider. And that would be your waves, superposition and double slit question answered.